Hi, everybody. Thank you for joining this webinar. My name is Majid Abnali Haidari. I'm the Technical Manager of Photonics, Technical Manager of Photonics at the Ozen Engineering. So today I want to discuss about how we can simulate the solar cell, how we can optimize it. So first of all, about the Ozen Engineering, we are expert in simulation of optics and photonics, structural, thermal, um, fluid and electromagnetic fields. So we offer a customer Ansys software consulting, training, mentoring, and technical support. So this is the outline of my talk. So first of all, I will discuss about the Ansys Lumerical, how Ansys Lumerical helps us to simulate just the solar cell, for instance, in this webinar. And what is our simulation methodology, how we can start. Because, for instance, the solar cell, so different part has a different part, like optical part and electrical part. So I will discuss about the optical simulation, how we can define a material, model, the source, boundary, how we can like set up the boundary. And I will just show a quick numerical demo of this part, and then I will discuss about the optoelectronic simulation, how we can define a doping and like how we can define a temperature, or if we have like multi-quantum well in our structure, how we can define it. So, and also then finally I will show some example of this area. So about the numerical. Lumerical has different packages. Like we have some solver in component level, and we have solver in circuit level. So because in this webinar, just we want to discuss about solar cell. So just we focus on component level. So in the component level, we have a different solver like FDTD, mode, theme, charge, heat, multi-quantum well. So these are useful for simulating the optical and optoelectronic simulation. For instance, FDTD mode and theme can be used for light propagation and modes in nanophotonic devices. You can calculate the transmission, absorption, scattering. You can calculate the dispersion parameters. So with the heat, you can simulate the heat. With the charge, you can define a doping, different doping, and you can like based on the drift diffusion equation, you can like simulate the bulk charge transport in the semiconductor devices. And with the multi-quantum well, you can simulate the quantum mechanical behavior in your device. So solar cell is very good example for this area, because with the solar cell, we have like optical part. So we need to calculate the absorption, and we have electrical part. We need to see how much of this photon generates electrons and holes. So we need a charge. And because sometimes also we need to simulate the heat. And if our structure includes like quantum wells, so we need multi-quantum well. You see that like this example, solar cell includes all of these solvers. And to simulate the solar cell, we need to use like FDTD, heat, charge, and multi-quantum well. So we have other tools, but these tools like we don't want to discuss about these tools, because, for instance, these tools is useful for circuit simulation. For instance, imagine that you have you designed a device based on a component level, and you want to use this component level in a circuit, and you want to see a circuit behavior like eye diagram, like see the spectrum. So, but in this part, in the solar cell, we just focus we'll focus on component level. So this is the concept of solar cell. So we have a solar spectrum, as you see here in this picture. So this is a solar cell, absorb the light from the sun, then convert the photon, absorb the photon, and generate the electron hole pairs, and then create a electricity, so power for us. So the final parameters that we need in the solar, so is a power. So we want to have a maximum power. Like if you look at this IV curve, so we want to bias our solar panel like in here. So in this point we have a maximum power. So, but how we can use a numerical tools to achieve a like maximum power? By the numerical tools, by the numerical FDTD, you can calculate the maximum, how much the power absorbed by the solar cell, and then with the numerical charge, you can calculate how much electricity generated with the like this the absorbed photons. So, but why we need to simulate the solar cell? Because if we want to increase the efficiency of the solar cell, we need to use a sub-wavelength patterning in our structure, like as you see in this picture, like nanowire, smooth eye surface, nanoparticle, photonic crystal. So these structure can improve our solar cell, but these results cannot be obtained analytically. We need to simulate, or we have other option. We can build the prototype, and based on that prototype, so we can design our structure. But we know that it's very expensive and time consuming in that case. So for the solar cell, we need FDTD, charge, and heat. So Lumerical is a 3D CAD environment capable to handling a complex geometry. You can create like nanostructure, grating structure, a structure with a gold, plasmonic structure. So it's a like 3D CAD environment, and you can define and you can insert experimental material or define uh, numerical library material, which has like optical and electrical characteristic. So what is the like physics behind the FDTD? So FDTD actually solves the Maxwell equation for broadband results just in one single simulation. And the charge solved the drift diffusion and Poisson equations, both 2D and 3D. So there is a good integration between the optical and electrical in the numerical workflow. How we can start in the solar simulation? We can start with FDTD. So in FDTD, like we can calculate absorbed power, optical efficiency, generation rate, and also ideal short circuit current density. So the generation rate that we have in FDTD goes to the charge. In the charge, we can calculate the IV curves, short circuit, short current circuit, like open voltage, recombination, if we have some recombination like Ozen, short grid holes, or our other recombination that we have, like, and also about finally we can calculate the photovoltaic efficiency. This is the whole workflow. For more information, also you can look at our knowledge base article at the Ansys website. So, but about the FDTD. So in the FDTD, the first step, we calculate the electric and magnetic fields. So we have these two fields. Based on the electric and magnetic field, we can calculate the absorbed power by this formula. So because we have electric field and we have an imaginary part of the like refractive index. So then based on the absorption power. So, and by assumption, because our system also is linear, so we can calculate the transfer function of the system by the impulse response. And by that we can calculate the photon generate in our structure. So in FDTD we assume that all the photon generate electron holes. So for this reason we say that it's the ideal case. For non-ideal case we need to bring this result to the numerical charge and calculate the results. So then this is the optical efficiency. It's number of absorbed photon divided to number of incident photons. So after we calculate the generation rate, then we can use the continuity equations, and we can calculate the electron hole density potential, and then after that we can calculate the electrical efficiency, which is defined by number of electron reaching electrodes to number of absorbed photons. And this is a final quantum efficiency that you can see in here. So we use a numerical charge to calculate these parameters. This is a simple example of just in one direction. This is a formula. So these two equations are continuity equation. These two equations, drift diffusion equation, and this is a Poisson equation. So what is the input for numerical charge? You see here, this is generation rate. So this generation rate, Jn and Jp, comes from the numerical FDTD. So the green color shows the material property. We can define it in the numerical charge, and also doping density. Also, we define the doping density in the numerical charge based on our inputs. So we can calculate the IV curves or fill factor or other parameter that is important for the solar cell simulation. A simple example. This is a planar silicon solar cell simulation with numerical. The first step is FDTD. In FDTD, we calculate the optical and heat generation rate profiles. So first, I will show a quick demo of how we can generate this profile with the FDTD, and then I will show a heat demo and then charge demo. So this is a workflow. The optical and heat generation goes to the heat generation goes to the heat part, and then we generate a temperature. So the input of charge is the temperature from the heat and the generation rate from the FDTD. So let's go to and see the demo. So for the demo, before we start the demo, first step, we need to define our geometry, define a material, then modeling a solar illumination, boundary condition, and then we can calculate the optical parameters, like here. This is a transmission. You see here, the red one is the absorption, the green is transmission, and the blue is reflection and this is a heat distribution. Let's look at the numerical demo. So here, so start. As you see here, we can design our geometry. So we can define our material. Like for instance, we select aluminum. We want to plot the aluminum. You see that we can put the minimum and maximum wavelengths. This is the real part, the imaginary part of the aluminum. So for instance, this is for silicon. You see that so this is a real part and imaginary part of the silicon. So after that, so this is our third layer. So next, we define our solver. Our solver is FDTD. So for instance, in this simulation, we use a 2D FDTD. The mesh setting is different. We have a different mesh setting. This is a boundary condition. We have a periodic boundary condition is a X domain. So, and then we need to a source. You see, we have a plane wave source here. And the type of our source is Bloch periodic. So the injection axis, if we change the injection, you see that how it looks like. So the range of frequency we can, and this is a monitor. We can put a different monitor in our structure. This is a solar generation rate that is exist in a Lumerical. So this is a script exists in a Lumerical. You can see that, for instance, here, the short circuit current value, this is ideal. And we can export the generation rate. This is a generation rate. And also this is a thermal. So we can export this thermal to the heat solver. Oh, there is a good a script environment that you can write your own code. For instance, here we write a code to calculate the transmission, absorption, and reflection. So these two files generate in our FDTD simulation, like one for heat and one for generation rate. So in the next step, we want to use these values in the Lumerical charge. Again, in the Lumerical charge, we need to define a geometry, material property, but in the material property, in the Lumerical charge, we can assign electrical property, thermal property, and optical property. And we can define a doping profile. And if we have multi-quantum well, we can define the quantum well structure. And also you can simulate the temperature part. And finally, I will show again a Lumerical demo. For instance, here you can see that this is a IV characteristic, and this is the power versus voltage. So so this is the environment of Lumerical charge. You can see that, for instance, just we want to simulate a charge simulation. We have option to do a steady state and dynamic simulation. So again, we can have option to like for the mesh. These are the results that we can see: band structure, charge doping, mobility, and if we have advanced options, so we can do it. And so here we can define a different doping, like constant diffusion, implant, and if we want to, we can import also doping from the outside. So like, for instance, here we want to define a doping in the P side. So this is a geometry of our doping, and so our doping time is type is P, and we can set the value and the different doping part you can see here. So in this part we can like import the generation rate and a temperature profile, and then we can simulate for different voltage. We can sweep different voltage, so we can do different simulation like with thermal effect or without thermal effect. And then this is our charge distribution. So again, we can write a script in this environment, like we want to plot the IV curve and plot the power. You see that this is the IV curve and this is a power efficiency that we can achieve with this numerical charge. Also, we can include different recombination. You see here, you can enable or disable this recombination. Like here, I enable the Auger, shotcrete, hold, and radiation. And after I simulate the like with the effect of recombination, we can see the our fill factor and our efficiency is decreased, as you see in this picture and in this video. Okay, so in the next step, we want to, like we used in the numerical charge, we use the output of heat, but we want to know how we can generate a temperature profile for the heat, for the charge. So we need to do some thermal simulation. You can see that, for instance, here to see the effect of thermal. So the blue one is the like the IV characteristic for the power for the effect of heat, and if we ignore the heat, you can see that the amount of power with the effect of the heat is decreased. So, and also this is the heat distribution, like for different temperatures. So let's look at the how we can calculate the heat by the numerical heat. So it's easy. Like we can import the heat parameters that we generate in a numerical FDTD. So we can define our boundary condition for the heat side. You see that? So we can define a monitors, and we can extract the data like for the numerical FDTD. You see that there is the file generated that we can use this one in the numerical charge, and this is the heat distribution through the numerical heat. So okay, now we know which solver and how we can define a material, geometry, monitor, solver. So let's look at some results. For instance, this is a silicon solar cell with MOS-I anti-reflection coating. So we have a geometry. This is our unit cell. So the green one shows the transmission, and the red one shows the like transmission to the substrate. The red one shows the absorption. You see that if we compare this plot with a flat structure, so without any periodic structure, you can see that the amount of absorption is increased because of the nanostructure in our surface. So, for instance, here we can see the absorption profile for the electric field in different wavelengths. So, for instance, this is 350 nanometer, around 500 nanometer, and 850 nanometer. You see that for 850 nanometer, the amount of absorbed power is much higher than, like, for instance, in 350. And if you look at this, you can see that the value of absorption here. So also you can use a plasmonic solar cell. Like, for instance, we have a periodic structure, and we have some nanoparticle in our solar cell. So you can go this knowledge base article for more information. Like these are the refractive real part and imaginary part of the our material, like silicon, gold, silver, and aluminum. You can see the effect here. This is our like spectrum versus wavelengths. This is the result for silver with the diameter of 100 nanometer and 200 nanometer. So the green one shows the diameter of 200 nanometers. So this is also for gold. You can see, for instance, and also this is the field distribution for the nanoparticle in the photonic crystal in the periodic structure, and this profile shows the field distribution without a nanoparticle. You see, without the like nanoparticle, you see that because of the plasmonic effect, we have a good enhancement light here that improve our efficiency, our solar cell efficiency. It's like here, this is for gold and this is for silver. So if you look at the spectrum versus wavelengths for the sun, you see that in this wavelength around 550 nanometers. So we have a peak power here. So like silver is a better candidate related to gold. So, and also this is the organic solar cell with photonic crystal. You see that we have a photonic crystal at top of the surface. So again, the real part and imaginary part of different material. So interesting here that like we have a photonic crystal. This is a band structure of photonic crystal for T and TM mode. So you see here in this point, we have a slow light. And because of the slow light, we have some enhancement in this region. So if you look at versus wavelength, you can see that we have a peak because of the slow light in this part. So I mean, sometimes we can use a band engineering of photonic crystal to enhance our solar panel efficiency. So we have plotted the field distribution in different regions. So like for instance, in A, B, C part. So what is the like the thing that we can see here, like we compared the result with a flat and photonic crystal with loss and photonic crystal without loss. So you can see that the effect of with the photonic crystal, we have like higher absorption related to in compared to the flat surface. So we can change the parameter, for instance, here to see the effect of solar cell performance, like here, the thickness of ITO. So I can change the thickness of ITO from 0.1 to 0.2 micrometer, and I can monitor the like number of absorbed photons. I mean, you have access to sweep and optimization module in the Lumerical, and you can do some analysis. Sometimes in your structure you have a quantum well. So if you have a quantum well in your structure, so there is actually dynamic link between a charge and multi-quantum well, and so just you can define your quantum well structure, and Lumerical charge can solve the Schrodinger equation and drift diffusion equation, and in a dynamic workflow, and also you can use a like similar previous example, you can use the output of FDTD. So this is the whole picture. I can show you in a solar. So but Ansys Lumerical For instance, if we want to simulate just a structure in nanoscale, in microscale, so Lumerical is good. But sometimes we want to simulate in a bigger picture, like in a ray tracing regime. So we have Zmax. And also, if you want to include the environment effect, so like effect of human vision, effect of foggy environment, dark environment. So I mean, we have a SPIOS, and there is a good workflow and a complete workflow in Ansys website that can use the Zmax, Lumerical, and SPIOS. For instance, here is a CMOS image sensor. So if you go to this example, this example, you can see that how this workflow works, how people can design, how designer can design a image sensor and then do the ray tracing and then do some human vision analysis. Or other example like meta lens or LED. Yeah. So if you have any questions, so please send the email to info@ozenic.com. And so this is our sales email. And if you need some training material, so you can contact with training@ozenic.com. And thank you. If you have any question, I'm happy to answer.